So welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we also do see and appreciate the beauty in the simpler problems. So today's problem comes from the MIT 2024 Integration B Semifinals number 1, problem 3, which is the definite integral from x equals to 0 to pi over 2 of sine of cotangent squared of x times sec squared or secant x secant squared of x. So this is a very interesting problem, as you will see as we solve it. It's a pretty intricate problem, but I hope you do enjoy our solution. But before I jump on to that, I'd like to thank our subscribers. Thank you so much for all the support that you've given us. We continue to grow, we continue to get excited about this journey that we started, and all thanks to you, our supporters and subscribers. I'd also like to thank our first-time visitors. What we do here at Everyday Mathematics is we go about and run and look for these very interesting problems, and then we come back with the solutions that we think do befit these problems. For our repeating visitors who haven't yet subscribed, we do really encourage you to consider subscribing to our channel. So first things first, what I would do with this problem here is I would like to express everything in form of tangent. So cotangent squared x is the same as 1 over tan squared x, and sec squared x is the same as 1 plus tan squared x. Then the next thing is I would say let u be equal to tan x such that du dx is the same as sec squared x, and therefore du over sec squared x is equals to dx. And so expressing sec squared x in form of u would be first of all to express sec squared x as 1 plus tan squared x, and therefore that means that since u is equal to tan x, that means du over 1 plus u squared is the same as dx, or can be replaced for dx. And so looking at this expression here, in place of tan squared x, we'll plug in u squared, and then this is obviously 1 plus u squared, but dx is the same as du plus 1, du over 1 plus u squared. So what we see here essentially is that this 1 plus u squared and this 1 plus u squared cancel out. One thing to note is that when x is 0, tangent of 0 is 0. So in other words, u is 0. As you can see here, when x is pi over 2, tangent of pi over 2 means that u tends to infinity, as we see here. So essentially we are left with an integral from u equals to 0 to u tending to infinity of sine of 1 over u squared. Very interesting problem. So this is where now things begin to become a little bit interesting. So the first thing that I would do is I would say let v be equal to 1 over u such that dv du is 1 over u squared, and therefore dv du is the same as, since v is the same as 1 over u squared, so dv du is the same as negative v squared, right? And so we can bring this down here such that negative dv over v squared is the same as du, right? Now, as obviously u, as when u equals to 0, v tends to infinity, and then when u tends to infinity, v equals to 0. And so keeping this negative sign in place, 1 over u squared is v squared, and then du becomes negative dv squared, negative dv over v squared, and then it results in this negative sign. Now, as it's known with many integration approaches, when you have a negative sign here, you can negate that by simply flipping the interval. And so now integrating from v equals to 0 to infinity, and then looking at this 1 over v squared. 1 over v squared is the same as the derivative of negative 1 over v. And so we're going to approach this as a partial, maybe integration by part problem. And how I would see that is this here is the same as du, and this here is the same as v, right? So now uv becomes negative 1 over v sine v squared, and since we have this negative here, now minus this becomes plus, and next we have 1 over v squared, 1 over v, and then the derivative dv is 2v cosine v squared. And as you can see, this and that cancel. And then the problem is, how do we approach this result here? Now, when v tends to infinity, this term here tends to 0, right? And then when v is 0, sine of v squared tends to 0. So this term here just goes to 0 at both intervals. And so we are left with now twice the integral of cosine v squared from v equals to 0 to infinity. Now this is the same as the real part of twice the integral of e to the power negative I v squared, since e to the power negative v squared is the same as cosine of v squared minus I sine of v squared, right? So, and this is the real part, this is the real part, and this is the imaginary part. Okay, so we are focused on the real part. So we can integrate this entire thing and then just pick out the real part. Now, what is interesting here is that now, since this is symmetrical about v equals to 0, if we take the entire thing from v tending to negative infinity to infinity, then this is just half of that. So we've introduced the constant half here, and this cancels with that. So we are left with the integral, the real part of the integral from negative infinity to infinity of e to the power negative I v squared. Now, using Gaussian integral, we know that when you integrate this is a general thing that everyone knows. When you're integrating e to the power negative x squared from negative infinity to positive to infinity, you have the square root of pi over a. And here our a tends to be I, so our answer here is pi over I square root. And then we want the real part of that. So I is, we can separate these things a little bit. Now, 1 over square root of I square root of I is the same as essentially square root of pi times I to the power negative a half. And I is the same as e to the power I pi over 2, since this becomes cosine pi over 2, plus I sine pi over 2. Sine pi over 2 is 1, so you have I. And now, so we have everything in I here encapsulated in this. And now we can multiply the powers so that now we get the real part of square root of pi times e to the power negative I pi over 4. So this 2 and 2, 4, and then the sign comes in here. So this, using Euler's expression, we get square root of pi into bracket cosine of pi over 4, which is 1 over root 2, minus I 1 over root 2. And as we can see, the real part is just this part, which is square root of pi over square root of 2, which is the same as square root of pi over 2. And that, my friends, is the answer that was provided. I hope we were very clear and succinct. If you have any question or if you have an alternative suggestion, I know that folks who could solve it using complex algebra and integrals, but using the basic concepts of calculus, this is how I propose we could solve it. So thank you again for the company you've given us. Until next time, à tout à l'heure et la prochaine fois.